Hello, my name is Pawel Dziewulski and the purpose of this video is to present and briefly discuss the main result of my paper, Eliciting the Just Noticeable Difference. In a nutshell, the article discusses the testable implications for a model of consumer choice in which the agent is unable to perfectly discriminate between similar options. I provide a method of inferring consumer preference from observable data and show how to evaluate the agent's cognitive inability to differentiate between options. Finally, I argue that the latter may serve as a natural measure of departures from utility maximization. In this short video, I restrict my attention to the main result of my research. Nevertheless, I encourage everyone to take a closer look at the paper. To download the most recent draft of my work and the presentation slides, please click the link in the description. To motivate my talk, I considered the following thought experiment by Luce. Suppose we offer 2 cups of coffee to a subject. In one of them, there is n grains of sugar. In the other one, there's n plus 1. Otherwise, the cups are identical. It is not controversial to assume that in such a case, the agent would behave as if he or she were indifferent between the 2 options, regardless of the value of n. After all, it is just a single grain of sugar which is barely noticeable. Following the evidence from psychophysics and the so-called Weber-Fechner law, the consumer would be unable to differentiate between the options unless the ratio of the amounts of sugar exceeded a particular value lambda, a noticeable difference. Note that such observations could not be explained by utility maximization. Clearly, any preferences representable by a utility function require for indifferences to be transitive. That is, if the agent is indifferent between n and n plus 1 grains of sugar, n plus 1 and n plus 2, and so on, then he or she would have to be indifferent between any amount of sugar in the coffee. In particular, the consumer would be indifferent between n and lambda times n grains. However, as it was pointed out on the previous slide, this would not be realistic. More importantly, assuming global indifference would not be very practical, as it would not allow for any predictions. Moreover, it is reasonable to assume that the choices observed in such an experiment do not reveal an actual indifference. Rather, they imply that the consumer does not see a difference between the options. Following the tradition of Afriat and Varian, suppose the researcher observes a finite number of choices from L goods, where a typical observation consists of a bundle X and the corresponding, possibly linear, budget set B. The purpose of this paper is threefold. First of all, given the observations, I provide a method of inferring the actual, true preferences of the consumer from the data when he or she cannot perfectly discern between options. Second of all, I show how to elicit a generalized, multidimensional notion of a noticeable difference lambda. Finally, I argue that the noticeable differences may serve as a measure of departures from rationality in terms of the agent's cognitive inability to differentiate between options. In this video, I focus solely on the second point. That is, I restrict my attention to a method of eliciting a noticeable difference. First, I introduce my notion of noticeable differences. Luce proposed an intuitive way of modeling choices with noticeable differences using semi-orders. Roughly speaking, a semi-order is an irreflexive binary relation P that can be represented by a utility function U in the following way. That is, option X is strictly preferred to Y if and only if the utility corresponding to X is sufficiently higher than the utility of Y, where the strictly positive threshold is normalized to 1. If neither X is preferred to Y, nor Y is preferred to X, or equivalently, the absolute value of the difference between utilities of X and Y is less than 1, we say that X is indistinguishable from Y and denoted by I. Specifically, note that the indifference relation I is not transitive. For a formal definition of a semi-order, please refer to the paper or the corresponding literature. We say that a set of observations is rationalizable with a noticeable difference lambda if there is a utility function u such that for any observation bx, if bundle y was available, then it could not be strictly preferred to x. Since this definition alone does not allow me to capture the noticeable difference, I restrict my attention to preferences for which bundle lambda prime times y is noticeably different and strictly preferred to y, for any lambda prime greater than the noticeable difference lambda. This is inspired by the previously stated Weber-Fechner law. In this case, the number lambda determines by how much one should increase the size of a bundle for the agent to be able to perceive the change. As I show in my paper, a useful feature of this model of consumer choice is that it is equivalent to utility maximization with thickened indifference curves. Consider the following model of consumer choice. For any observation bx and a non-zero bundle z, if z yields higher utility than x, then lambda times z must be strictly preferred to any bundle y that was available when the choice x was made. To explain this on a graph, suppose that bundle x was chosen from set B. Clearly, it does not maximize the utility as there is another bundle y which shifts the consumer onto a higher indifference curve. However, bundle x is optimal in our sense, since for any bundle z that yields a weakly higher utility than x, lambda times z lays above the indifference curve intersecting y. Thus, unless the indifference curves intersecting x and y are sufficiently far apart, bundle x remains optimal in our sense. Therefore, this model of choice assumes that whenever the agent is making a comparison, he or she behaves as if his or her indifference curves were thick, where the thickness is given by scaling the original indifference curve by lambda. This specification of the model allows us to pin down both the true preferences of the agent, which are given by the map of the original indifference curves, as well as the noticeable difference, which determines the thickness of indifference curves the agent is using when comparing options. Finally, this model highlights the sense in which lambda could measure departures from rationality. The closer the parameter is to 1, the thinner are the indifference curves, and the closer are the choices of the consumer to those of the utility maximizer. Having stated the definition, I now show how to infer the noticeable difference. Before I dive into the details, I find it convenient to make a short digression and recall the classical result by Afriat that determines the necessary and sufficient conditions under which a set of observations can be rationalized by a locally non-satiated utility function. A set of observations, defined as previously, is rationalizable by a utility function u if and only if, for any observation bx, bundle x yields a higher utility than any other available bundle y. Afriat and Varian provided a necessary and sufficient condition on the set of observations, the so-called generalized axiom of revealed preference, under which it can be rationalized by a locally non-satiated utility function. GARP requires that for any sequence of indices, such that bundle from observation B was available in observation A, bundle from observation C was available in observation B, and so on, till we close the cycle, that is, the bundle from observation A was available in observation Z, every bundle XS must be in the upper bound of the corresponding budget set BT. That is, the bundle from observation B has to be in the upper bound of the budget set from observation A, the bundle from observation C has to be in the upper bound of the budget set from observation B, and so on. Since this condition is both necessary and sufficient for a set of observations to be rationalizable by a locally non-satiated utility function, it exhausts all the observable implications of this model. Consider the following example. Notice that this set of observations violates GARP. In fact, we have at least one cycle where bundle x1 was available in observation 2 and bundle x2 was available in observation 1, but neither x1 belonged to the upper bound of B2 nor x2 was in the upper bound of B1. In fact, such observations could not be rationalized by a locally unsatiated utility function. Since bundle x2 was chosen from the set B2, while bundle x1 was in the interior of the budget set, local non-satiation implies that bundle x2 was strictly preferred to x1. Similarly, bundle x1 had to be strictly preferred to x2. However, this leads to a contradiction. But let's go back to the problem of noticeable differences. The principal question of this paper is, under what conditions can we rationalize a set of observations with a noticeable difference lambda? That is, under what conditions imposed on the set of observations can we guarantee that it can be explained with a model of consumer choice with thick indifference curves, where the thickness is determined by the parameter lambda? My principal axiom states that a set of observations obeys the condition for lambda if for any cycle such that the choice in observation B was available in observation A, the choice in observation C was available in observation B, and so on, the sum of numbers KTS along the cycle does not exceed the total number of elements in the cycle, where the number KTS is the minimal integer k for which we can scale the budget set BT by lambda without excluding the bundle XS. Note that, by construction, since each element XS belongs to the set BT along the cycle, all such numbers must be negative. Hence, such numbers determine how many times can we scale down the budget set BT by lambda without excluding XS. Equivalently, this condition requires that, for any cycle induced by the set of observations, the average number of shifts KTS must be strictly less than 1. To better explain the condition, consider the set of observations discussed earlier. We already know that this set cannot be rationalized by a locally non-satiated utility function. Is it possible that it is rationalizable with a noticeable difference lambda? We have to check whether it satisfies the axiom presented on the previous slide. Take some lambda strictly greater than 1. We know that there is one cycle such that x1 belongs to B2 and x2 is in B1. Therefore, we need to evaluate the numbers KTS for each pair in the cycle. To evaluate K12, we need to check how many times can we scale down the set B1 without excluding x2. Notice that if we scale down the set by lambda once, we already exclude x2 from the set. Thus, we can scale the set at most 0 times, which means that K12 is equal to 0. Next, I turn to K21. How many times can we scale B2 by lambda without excluding x1? We can scale it once, but 2 is 1 too many. Therefore, K21 is equal to -1. To verify the condition, it suffices to take the negative of the sum of the two integers and see if it is strictly less than the number of elements in the cycle, which is 2. And it is. It turns out that the condition exhausts all the testable implications of noticeable differences. My main result states that a set of observations can be rationalized with a noticeable difference lambda if and only if it obeys the axiom for the same value of lambda. In addition, I show that the corresponding utility function is well behaved. That is, it is continuous and increasing. Moreover, if all the choices were made from co-convex budget sets, then the function would also be quasi-concave. This is to say that, in this framework, the above properties of the utility function are not testable. In some sense, we get them for free. For those who are interested in the proof of the main result, please refer to the paper. Nevertheless, I would like to discuss the main idea behind the necessity of the axiom for this form of rationalization. Suppose that a set of observations is rationalizable with a noticeable difference lambda and some utility function u. Take any sequence S such that bundle xb belongs to BA, bundle xc is in BB, and so on. In particular, it need not be a cycle. That is, bundle XA need not coincide with XZ. It can be shown that whenever the sum of the corresponding integers kts along the sequence is weakly greater than the number of elements in the sequence, then it must be that the utility of the bundle XA is strictly greater than the utility of bundle XZ. In other words, whenever the sum of numbers kts is greater than the number of elements in the sequence, then bundle XA is revealed strictly preferred to XZ. Clearly, this excludes the possibility that S is a cycle, as XA cannot be strictly preferred to itself. Please consult the paper for the complete argument. We find it instructive to state some basic properties of noticeable differences. First of all, it is easy to show that for any set of observations, there is a sufficiently large noticeable difference lambda for which the set is rationalizable. Second of all, whenever a set of observations is rationalizable with some noticeable difference lambda, it can be rationalized with any larger value of the noticeable difference. Thus, the interest of the researcher may be restricted to the least value of the noticeable difference for which the set is rationalizable. This brings me to the next observation, namely, a dataset satisfies GARP if and only if it obeys my axiom for all lambdas strictly greater than 1. Therefore, a set is rationalizable by a locally non-satiated utility function if and only if it can be rationalized for a noticeable difference arbitrarily close to 1. This highlights the intuition presented in one of the initial slides. The lower is the noticeable difference, the closer is the dataset to being rationalizable by maximization of a locally non-satiated utility function. Equivalently, the closer is the noticeable difference to 1, the thinner become the indifference curves that the agent is using when comparing options. Therefore, lambda may in fact serve as a measure of departures from rationality. Please refer to the paper for an extended discussion on the properties of this measure and its comparison to the existing measures of GARP violations. Finally, our test is implementable, as it can be performed by applying a computationally efficient algorithm. In fact, an important feature of our result is that it can be applied directly to empirical data. I would like to conclude this presentation with an empirical illustration of our methods. We implemented our test to a household-level scanner panel data. The panel contained monthly grocery expenditures of 494 households, with 26 monthly observations per household. For each subject, an observation consisted of a linear budget set BT, like in the original framework of Afriat or Varian, where prices PT were the observed shelf prices, and the corresponding choices XT. For details regarding this set, see the paper by Eczenika Lee and Shum, who performed their analysis on the same dataset. In the preliminary analysis, we determined that 396 out of the 494 households violated GARP. Therefore, choices of almost 80% of the available households could not be explained with utility maximization. In our main analysis, for each household, we evaluate the infimum over all noticeable differences that could rationalize the observable choices. Henceforth, we refer to this value as the just noticeable difference. The following table summarizes our results. Whenever we considered only those households whose choices violated GARB, the mean just noticeable difference in the sample was close to 1.09. This means that a 9% increase in the size of a bundle was sufficient for an average agent to notice the change. The median was around 1.07. Whenever all households were included in the sample, including those whose choices satisfied GARB, the distribution shifted to the left. This is because, by our previous observation, for any rationalizable set of observations, the corresponding just noticeable difference is equal to 1. For this sample, the mean dropped to around 1.07 and the median to around 1.05. The whole distribution is represented in the following graph. Thank you for listening. You can download the most recent draft of the paper and the presentation slides by clicking on the link in the description. Any comments, suggestions, or questions are welcome. You can find the contact details on my website. The link is provided in the description.